You've been told since middle school that friction is simple. Two surfaces in contact, a force holding them together, a coefficient you look up in a table. Multiply, then you're done. Move on to the next problem. But here's the thing. Friction is one of the oldest unsolved problems in physics. We've been studying it for over 500 years, and we still don't have a complete theory of why it works. We have rules. We have approximations. We have numbers that match experiments. But why underneath it all? That's still an open question. And I want to show you something about static friction specifically, the force that keeps things still, that once you really understand it, will change the way you think about every object sitting on every surface you've ever seen. Let me start with what everyone thinks they know. You put a book on a table. The book doesn't move. You push the book gently. It still doesn't move. You push harder. Still nothing. Then at some specific force, the book lurches forward and starts sliding. That transition, from still to moving, is governed by what we call static friction. And the story you were told goes like this. There's a maximum force that static friction can exert. It equals the coefficient of static friction, mus, times the normal force. Once your push exceeds that maximum, the object breaks free and starts to move. Simple. Clean. What did I say? Mind sometime. Predictable. And wrong. Why? It is strangely adsurvives. Or rather, incomplete in ways that matter enormously. Let me show you why. Here's the first strange thing about static friction that almost no one talks about. Static friction is not a fixed force. It's a reactive force. It matches whatever you do up to a limit. Think about that. You push with 1 Newton, static friction pushes back with 1 Newton. You push with 5 newtons, it pushes back with 5. You push with 9.9 newtons, it pushes back with 9.9. It's like an invisible hand on the other side of the object that exactly mirrors your effort. How does it know? Seriously? How does the surface know exactly how hard you're pushing and respond with precisely the right amount of force to keep the object stationary? This isn't a spring. There's no mechanism that obviously measures your applied force and generates an equal response. And yet it does. Every single time. Perfectly. This is Newton's third law operating through a contact interaction. Yes. But the deeper question is, what physical mechanism at the surface is capable of this perfect instantaneous adaptation? And here's where we have to go small. Microscopically small. If you could zoom in on the surface where your book meets the table, I mean really zoom in, down to the scale of micrometers, you would not see 2 flat planes in contact. You would see a landscape, mountains and valleys, peaks and ridges. The surface of even the smoothest looking material is a jagged, chaotic terrain at the microscope. These are called asperities, tiny bumps. And when 2 surfaces are placed together, they don't actually touch everywhere. They touch only at the tips of these asperities. The real contact area, the area where atoms are actually close enough to interact, is a tiny fraction of the apparent contact area, sometimes less than 1%. So when your book sits on the table, it's not resting on a flat plane. It's balanced on thousands of tiny mountain peaks. And at each of those peaks, the atoms of one surface are pressing against the atoms of the other surface, and they're forming temporary bonds. Weak bonds. Weak. Chemical bonds of a sort. Van der Waals interactions. Sometimes even called welding at the atomic scale. Static friction is, at its root, the collective strength of thousands of microscopic welds. Now here's where it gets interesting. When you push gently on the book, you're not actually keeping it perfectly still. At the microscale, things are happening. The asperities are deforming. They're bending. Some of them are stretching. The real contact points are under shear stress, and they're responding elastically, like tiny springs being pulled sideways. The book looks still to you, but at the contact interface there's a silent war happening. Forces are being distributed, absorbed, redirected through a complex network of microscopic contacts, each one bearing a tiny fraction of your applied load. And as you push harder, some of those contacts start to fail. Individual asperities reach their breaking point and snap. But here's the key. When one breaks, the load it was carrying gets redistributed to its neighbors. And if those neighbors can handle the extra load, the book stays still. The system adapts. This is why static friction can match your force. It's not one mechanism. It's a collective, a democracy of microscopic contacts, voting in real time on whether to hold or release. And the maximum static friction force that most times you learned about, that's the point where enough contacts have failed that the remaining ones can't carry the redistributed load. It's a cascade, a tipping point, a phase transition, almost. One contact fails. Two more take its place. You push harder. 10 fail. 90 down. Now, 0. 20 take over. You push harder still. 100 fail. The remaining contacts are now overloaded. They fail in rapid succession. The cascade becomes unstoppable, and the book moves. That's what breaking the law of static friction actually means. You didn't overcome a single force. You collapsed a network. You triggered an avalanche at the microscale. Now stop right there, because this has an immediate and profound implication that the simple equation, most times, completely hides from you. If static friction depends on these microscopic contacts, and those contacts depend on the specific arrangement of asperities, and that arrangement depends on the history of how the surfaces were brought together, how long they've been in contact, the temperature, the humidity, whether there are contaminants, whether the surfaces have been polished or roughened. It's a property of a specific interface at a specific moment in time. And this is experimentally verified. If you place two surfaces together and wait, the static friction between them increases over time. It's called aging. And in aging, the contacts creep. They deform plastically. They grow. New contacts form as surfaces, settle into each other. The longer you wait, the harder it is to break the object free. This is why a book that's been sitting on a shelf for a year feels slightly stuck when you first try to slide it. It's not your imagination. The interface has aged. The microscopic welds have strengthened. And here's another thing the simple equation doesn't tell you. The transition from static to kinetic friction, from still to sliding, is not instantaneous, and it's not uniform. When you finally push hard enough to break static friction, the entire contact interface doesn't fail at once. It fails in a wave. A crack-like front propagates across the interface, starting at one edge and racing to the other, just like a crack propagating through a solid material. This was only definitively shown experimentally in the early 2000s. Researchers at the Weizmann Institute and elsewhere use high-speed cameras and embedded sensors to watch the transition happen in real time, and what they saw was stunning. The onset of sliding is not as simple. Overcome the force and go. It's a rupture, a fracture event. The interface between two surfaces in static contact behaves mechanically like a solid, and when you break static friction, you're fracturing that solid. There are different modes of this rupture too. Sometimes the crack propagates slowly, sub-Rayleigh speeds they call it. Sometimes it moves fast, at the speed of sound in the material. And sometimes, and this is the truly wild part, it moves faster than the shear wave speed. It goes supersonic. It becomes what's called a super shear rupture. Wait. A supersonic crack between a book and a table? Yes. At the microscale in the right conditions. The failure front that initiates sliding can propagate faster than the speed of sound in the material. This is the same physics that governs earthquakes, the same rupture dynamics, the same mathematics. And this is not a coincidence. An earthquake is, at its most fundamental level, a failure of static friction. Two tectonic plates are pressed together. They're locked by static friction along a fault. Stress builds. The microscopic contacts along the fault are loaded, one by one, until the cascade begins. A rupture front propagates along the fault, releasing stored elastic energy as seismic waves. An earthquake is what happens when the Earth breaks the law of static friction. The same physics. The same rupture. It's just scaled up by a factor of 1 billion. Think about that. The same mechanism that lets you slide a glass across a bar counter is the mechanism that levels cities. The difference is scale, not kind. Now let me take you deeper. Because we've been talking about what happens when you break static friction, but we haven't talked about the most fundamental question of all. Why does the coefficient of static friction exist in the first place? Why is there a simple proportionality between the maximum friction force and the normal force? Why does that work? This is one of the most deceptively simple relationships in physics, and its explanation is beautiful. Here's the logic. When you press two surfaces together harder, increase the normal force. You might think this increases friction because the surfaces are being squeezed together more tightly, making it harder to slide them. And in a vague sense, that's true. Wow. But the precise mechanism is this. When you increase the normal force, the asperities at the contact points are compressed more. They deform. They flatten. And as they flatten, the real contact area increases. More atomic scale contacts are formed. More microscopic welds exist. The friction force is proportional to the normal force because the real contact area is proportional to the normal force. This is called Boden and Tabor's theory from the 1950s, and it relies on a key insight. The asperities deform plastically under the enormous local pressures of their tips. Even for materials that seem hard and rigid at the macro scale, the stresses at individual asperity contacts are so high because the contact area is so small that the material yields locally. And for plastic deformation, there's a simple relationship. The real contact area equals the normal force divided by the hardness of the softer material. That's it. That's where the proportionality comes from. The coefficient of friction, then, is not some mysterious material property. It's the ratio of the shear strength of the interface to the hardness of the material. It's a ratio of two material properties expressed as a single dimensionless number. And this is why mu doesn't depend on the apparent contact area. It doesn't matter if your book is big or small. What matters is the real contact area, which is determined by the normal force and the material hardness, not by the geometric size of the surfaces. This was one of the great puzzles of friction for centuries. Amontons noticed it in 1699. The friction force doesn't depend on the apparent size of the contact. It seemed bizarre. It seemed like a coincidence, But it's not. It's a direct consequence of the plastic deformation of asperities. Now, I want to take one more step into the strange. Because everything I've told you so far, the asperities, the real contact area, the plastic deformation, the rupture dynamics, all of this is the classical picture, the continuum mechanics picture barneys, and it works beautifully for most engineering applications. I'd best intended modifications, but there's a frontier, a place where even this picture breaks down. What happens when you make surfaces so smooth that there are no asperities? What happens at the atomic scale, where roughness doesn't mean random bumps, but means the discrete lattice of atoms themselves? This is the world of nanotribology. Friction at the nanoscale, more and it's strange. At the nanoscale, friction doesn't follow Amonton's laws. The friction force is not simply proportional to the normal force. It depends on the commensurability of the two crystal lattices in contact. If the atoms of one surface line up with the atoms of the other, if their lattice spacings match, friction is high. The surfaces lock together. But if the lattices are incommensurate, if they don't match, if one is rotated relative to the other, something remarkable happens. Friction nearly vanishes. This is called superlubricity, and it was predicted theoretically before it was observed experimentally. The idea is simple. If the atoms of one surface don't line up with the atoms of the other, then, at any given moment, some atoms are being pushed forward while others are being pushed backward. The forces cancel. It means there's no net resistance to sliding. It's like trying to push two egg cartons past each other. If the bumps line up, peak meets peak, they lock. But if you rotate one egg carton by an arbitrary angle, the bumps of one fall into the valleys of the other, at random. No locking, no resistance. They glide. Superlubricity has been demonstrated experimentally with graphite flakes, with carbon nanotubes, with other layered materials. And it's not just a curiosity. It's potentially revolutionary for engineering. Imagine bearings with essentially zero friction, machines that never wear out. Energy that's never lost to heat at sliding interfaces. But here's the catch. Superlubricity is fragile. Any contamination, a single layer of water molecules, a speck of dust, a chemical reaction at the surface, destroys the delicate cancellation of atomic forces. Real-world surfaces are messy. They're contaminated. They're rough. And so, for now, superlubricity remains mostly a laboratory phenomenon, but it tells us something profound about the nature of friction itself. Friction is not a fundamental force. It's not like gravity or electromagnetism. It's emergent. It arises from the collective behavior of billions of atomic interactions at an interface. And under the right conditions, the right geometry, the right cleanliness, the right alignment, it can be made to disappear entirely. Friction is not a law of nature. It's a consequence of disorder. Let me say that again. How do I say it? Friction exists because surfaces are disordered, because atoms don't line up, because real materials have defects and roughness and contamination. Once, in a perfect world, a world of mathematically ideal crystal surfaces in perfect vacuum, friction could be zero. But we don't live in that world. We live in a world of entropy and disorder and contamination. And so friction is everywhere. It's inescapable. It's woven into the fabric of our macroscopic reality, precisely because our reality is messy. And this connects to something even deep. The second law of thermodynamics. Entropy. Entropy. When you slide one surface against another, the kinetic energy of motion is converted into heat. The ordered motion of the object is converted into the disordered motion of atoms. Energy is dissipated. Entropy increases. This is irreversible. You cannot unslide the surfaces and recover the heat as kinetic energy. Friction is, at its thermodynamic core, a mechanism for increasing entropy. It's one of nature's primary tools for converting order into disorder, for turning useful energy into waste heat, for enforcing the arrow of time. When you break static friction and set an object sliding, you are initiating an irreversible process. You are creating entropy. You are participating in the heat death of the universe, one microscopic rupture at a time. That's dramatic, I know, but it's true. Now, let me bring this back to you, to your body, to your life. The reason you can walk is static friction. Every step you take, your foot pushes backward against the ground, and static friction pushes you forward. Without it, your foot would slip like walking on ice. The reason you can hold a glass of water is static friction between your fingers and the glass. The reason your car can turn a corner is static friction between the tires and the road. Static friction is not just some equation in a physics textbook. It's the force that makes terrestrial life possible. It's the force that gives you purchase on the world. That lets you exert your will on physical object. That lets you grip, climb, walk, run, build, and create. And every time you do any of those things, you're relying on thousands of microscopic welds forming and holding at the interface between you and the world. Temporary bonds. Fragile connections. A negotiation between surfaces at the atomic scale. You are held in place by the same physics that holds tectonic plates in place. The difference is that when your foot slips on ice, it's a minor embarrassment. When a tectonic plate slips, it's a catastrophe. But the physics is identical. Now, here's what I want you to sit with. The equation F equals mass times is not a law in the way that Newton's second law is a law. It's an approximation. A very good one, in most cases, but it hides a universe of complexity beneath its simplicity. It hides the fact that mousse is not a constant. It depends on surface preparation, sliding history, contact time, temperature, humidity, speed of loading, and a dozen other variables. It hides the fact that the transition from static to kinetic is not a simple threshold event, but a complex rupture process with dynamics that mirror earthquake physics. It hides the fact that the real contact area is a tiny fraction of the apparent area, and that all the action happens at asperity tips under enormous local stresses. It hides the fact that at the nanoscale, friction is governed by atomic lattice geometry and can, under ideal conditions, vanish entirely. And it hides the deepest fact of all, that friction is not fundamental. It's emergent. It arises from disorder. It's a macroscopic manifestation of microscopic chaos. So when I say I broke the law of static friction, what I really mean is this. I looked beneath the equation and found that the law was never really a law at all. It was a summary, a useful compression of an enormously complex reality into a single number and a single proportionality. And that's fine. That's what physics does. It compresses. It simplifies. It gives you tools that work without requiring you to understand every atomic interaction at every contact point. But if you want to understand, truly understand, why the book doesn't move, and then why it suddenly does, you have to go deeper. You have to leave the comfort of the equation and enter the chaotic, dynamic, beautiful world of real surfaces in real contact. Let me give you one more thought experiment. One more thing to consider. Imagine you have a heavy block sitting on a surface. You attach a force sensor and begin to pull, very slowly increasing the applied force. The block doesn't move. The force sensor reads 1 Newton, 2, 3, 4, 5, 6. At 7 newtons, the block breaks free. Simple experiment. Classic result. Now do it again. Same block, same surface, same everything, as far as you can tell. Pull again, slowly. This time, the block breaks free at 630 newtons. Again, 6.8. Again, 7.2. Kawai say, makes sense to do. Again. 7. Now, again, 6.5. New 6. The static friction force is not the same every time. It varies. It fluctuates. It's stochastic. Why? Because the microscopic arrangement of asperities is slightly different each time you place the block. Because the contacts have a random geometry. Why? Because thermal fluctuations at the atomic scale affect when individual welds break. Because friction, at its core, is a statistical phenomenon. The coefficient of static friction is not a precise number. It's a statistical average of a deeply random process. When you look up moose in a table and find steel on steel, 0.74, that's not a law of nature. That's a summary of thousands of experiments averaged together with error bars that nobody tells you about. And in most engineering contexts, this doesn't matter. You build in safety factors. Why? You over-design. You accept that moose might be a little higher or lower than the table value. And you make sure your bridge doesn't fail regardless. But in some contexts, it matters enormously. In earthquake prediction, for instance, you want to know when a fault will slip. You want to know the precise static friction force holding it in place. But you can't, because it's fundamentally statistical. It varies. It fluctuates. And it depends on details of the contact geometry that you cannot measure and cannot predict. This is one of the deep reasons why earthquake prediction remains so difficult. It's not just that faults are big and complex. It's that friction itself, the fundamental mechanism holding the fault locked, is inherently variable. It's a roll of the dice at the microscale, with consequences at the continental scale. There's a concept in this field called rate and state friction. It's an attempt to capture the time-dependent, history-dependent nature of real friction in a mathematical framework. The basic idea is that the friction coefficient depends on two things: the rate of sliding, how fast the surfaces are moving relative to each other, and a state variable that encodes the history of the contact, how long the surfaces have been in static contact, how the contact has evolved over time. The equations are empirical, meaning they're fit to experimental data, not derived from first principles. And they work remarkably well for describing a whole range of frictional phenomena, from the gradual strengthening of a static contact over time, to the weakening that occurs at high sliding speeds, to the complex stick-slip behavior that you see in everything from squeaky doors to seismic fault zones. Stick-slip, unwise, trilony, Nay, let me dwell on that for a moment, because it's something you experience every day without realizing it's a friction phenomenon. You're in a car. You step on the brakes gently. The car shudders slightly. I didn't know what to say. I said, that's stick slip. The brake pad alternates between gripping the rotor, sticking, and sliding, slipping, creating vibrations. You draw a bow across a violin string. The bow sticks to the string, pulls it, then slips. The string snaps back. Vibrations is sense more made to the string snaps back. The bow catches it again. Stick, nouns, slip, dialogues, stick, nymons, slip, bins, 100 times per second. And that oscillation, that periodic breaking and reforming of static friction, is what produces the sound. Music is made of friction. Arms. A door creaks. Ah! That stick slip at the hinge. Clock squeaks on a blackboard. Stick slip. I don't do not see it. I've been saying it. Tires screech. Stick slip. Deal. The earth quakes. Mission. Not on. Somete. Stick slip. Benishin. I don't want this. You staff. It's everywhere. This rhythmic breaking and re-establishing of static friction is one of the most ubiquitous dynamical phenomena in the physical world, and it arises directly from the fact that static friction is greater than kinetic friction. Think about why that creates oscillations. The object is stuck. You apply a force. Metazans. The force builds in whatever elastic element is connecting you to the object. A spring, your arm, the elastic deformation of the object itself. The stored elastic energy increases. At some point, the force exceeds the static friction threshold. The object breaks free and begins to slide. But now it's sliding and kinetic friction is lower than static friction. So the net force on the object is suddenly larger than the elastic element expected. The object accelerates. It overshoots. The spring or elastic element relaxes. The applied force drops, and eventually the object decelerates and stops. But now it's stopped again. Static friction re-engages. The elastic element begins to load again, and the cycle repeats. No. This is a limit cycle, a self-sustaining oscillation, driven by the difference between static and kinetic friction, and the frequency and amplitude of the oscillation depend on the elastic properties of the system, the mass of the object, and the friction characteristics of the interface. This is the physics of violin music. Not chais. This is the physics of earthquakes. This is the physics of industrial chatter in machining, of brake squeal, of tectonic tremor, all manifestations of the same underlying dynamical instability, created by the simple fact that static friction is higher than kinetic friction. And why is static friction higher than kinetic friction? Go back to the asperities. When surfaces are in static contact, the asperity junctions have time to grow, to deform plastically, to strengthen. The real contact area increases with time. More bonds form. The interface becomes stronger. But when surfaces are sliding, the junctions are being constantly broken and reformed. New contacts form, but they don't have time to age and strengthen before they're sheared apart again. The average junction is weaker. The real contact area is smaller. The friction force is lower. Time. That's the crucial variable. Static friction is higher because static contacts have had time to get stronger. And this leads to one of the most counterintuitive predictions of rates and state friction theory. If you take two surfaces that have been in static contact for a very long time, years, decades, centuries, the static friction between them should be very high, much higher than if they'd only been in contact for seconds. This is observed in fault mechanics. Faults that have been locked for a long time, that haven't had an earthquake in centuries, tend to produce larger earthquakes when they finally rupture, because the contacts along the fault have had centuries to age and strengthen. More elastic energy can build up before the rupture occurs, and when it does, the energy release is proportionally greater. The longer the silence, the louder the break. There's something poetic about that, something almost narrative. The world holds still, accumulates stress in secret, and then releases it all at once in a catastrophic rupture. This is the story of static friction, told at every scale from the atomic to the continental. Now, let me address something that might be nagging at you. I've been talking about friction as if it's purely a mechanical phenomenon. Bumps, interlocking, surfaces welding, more surfaces welding, cracks propagating, Western weather, all very physical, it's very tangible. But there's another school of thought, another way to think about friction that approaches it from the perspective of energy and thermodynamics. When you try to slide one surface against another, you're asking the system to move from one energy state to another. And the energy landscape of two surfaces in contact is not smooth. It's corrugated. There are energy barriers, little hills that the system has to climb over in order to move from one position to the next. At the atomic scale, these energy barriers correspond to the periodic potential created by the crystal lattice. Atoms in one surface sit in the potential wells created by atoms in the other surface. To slide, they have to climb out of one well and fall into the next. That climbing requires energy. That's friction. This is the Prandtl-Tomlinson model, one of the oldest and simplest models of atomic scale friction. And it captures something beautiful. Friction is the cost of moving through a corrugated energy landscape. And here's where it connects to thermodynamics. At finite temperature, atoms have thermal energy. They're jiggling, they're vibrating, and sometimes that thermal energy is enough to help them hop over the energy barriers without an applied force. This is called thermally activated friction, or sometimes creep. It means that at very low forces below the static friction threshold, there's still a tiny, tiny probability of the system moving. It's not zero. It's exponentially small, but it's not zero. The system can creep, atom by atom, over the energy barriers, assisted by thermal fluctuations. In this picture, static friction is not an absolute law. It's a very, very strong tendency to stay put. An overwhelmingly probable outcome, but not a certainty. At the atomic scale, in the fullness of time, even a static object can drift. This is related to something called the fluctuation theorem in statistical mechanics. At the microscale, the second law of thermodynamics is not absolute. It's statistical. There are rare fleeting moments where entropy decreases locally, where thermal fluctuations conspire to push a system uphill against the usual thermodynamic gradient. And friction, being a thermodynamic phenomenon, participates in these fluctuations. At the nanoscale, friction is noisy. It fluctuates. individual atomic slip events, are random and thermally activated. The clean, deterministic picture of force exceeds threshold. Object moves is revealed to be a macroscopic approximation of an inherently stochastic microscale reality. This is not just theoretical navel-gazing. It matters for nanotechnology. But for MEMS devices, microelectromechanical systems, where the moving parts are so small that thermal fluctuations in friction become significant, where the static friction force is not a well-defined number because the system is constantly exploring its energy landscape through thermal activation. At this scale, the boundary between stuck and sliding becomes blurry. It's not a sharp transition. It's a gradual crossover from thermally activated creep to steady-state sliding. The concept of a static friction coefficient starts to lose its meaning. And this brings us to the deepest philosophical point about friction, and maybe about physics in general. Laws are approximations. The law of static friction, F less than or equal to mus times n, is not a law in the same sense that conservation of energy is a law. It's an empirical regularity, a pattern observed at the macro scale. It emerges from the collective behavior of billions of microscopic degrees of freedom. And like all emergent phenomena, it has limits, boundaries where it breaks down. Also shows regimes where it fails. At very small scales, it fails because thermal fluctuations dominate. At very clean scales, it fails because superlubricity can occur. At very long time scales, it fails because contacts age and the coefficient changes. At the transition point, it fails because the onset of sliding is a complex rupture, not a simple threshold. The law works beautifully in the middle. In the regime of everyday life, at the scale of books on tables and feet, on floors and tires on roads. And that's enough. That's physics. You find the regime where your approximation works, and you use it. You don't pretend it's fundamental. You don't pretend it's exact. You acknowledge that beneath the simplicity lies a universe of complexity, and you accept that your equation is a map, not the territory. But, and this is important, the map is extraordinarily useful. The fact that friction can be summarized, approximately, by a single, dimensionless number for each pair of materials is one of the most useful facts in engineering. It lets you design brakes and clutches and tires and bearings and foundations and climbing equipment and everything else that relies on surfaces gripping or sliding against each other. The simplicity of the friction law is not a flaw. It's a gift, a compression of reality that lets you build things without needing to simulate every atomic interaction at every contact point. But if you want to understand, if you want to see what's really happening at the interface between you and the world, you have to go deeper. You have to look at the asperities, the junctions, the ruptures, the waves, the energy landscapes, the thermal fluctuations, the aging, the memory. And when you do, you find something remarkable. You find that friction, this most mundane, everyday, taken for granted phenomenon, is actually a window into some of the deepest questions in physics. How do microscale interactions give rise to macroscale laws? How does disorder create predictability? How does irreversibility emerge from reversible dynamics? How does a simple number encode the behavior of billions of atoms? These are not just questions about friction. These are questions about emergence, about statistical mechanics. About statistical mechanics, about the relationship between the microscopic and the macroscopic, about how the universe constructs the reality we experience from the chaos of atoms. Friction is a microcosm of physics itself. So, What happened when I broke the law of static friction? I pushed past the threshold. I triggered the cascade. I collapsed the network of microscopic welds holding two surfaces together. I initiated a rupture that propagated across the interface at speeds that can range from 0 to supersonic. I converted elastic potential energy into kinetic energy, and then, through kinetic friction, into heat. I increased the entropy of the universe by a tiny amount. I participated in the irreversible march toward equilibrium that defines the arrow of time, and the book slid across the table. That's what happened. It looked simple. It felt simple. The equation said it would be simple. But underneath, it was a rupture, unmade, a tension, an earthquake, a phase transition. A collective failure of 1,000 atomic bonds, an irreversible thermodynamic event. A statistical fluctuation made macroscopic. The simplest thing in the world, pushing a book across a table, contains within it the physics of earthquakes, the mathematics of fracture mechanics, the thermodynamics of irreversibility, the nanoscience of atomic lattices, and the deep philosophy of emergent laws. We can calculate it, we can use it, we can engineer with it, we can predict, roughly, when the book will move and how hard you need to push. But do we fully understand it? Do we have a complete first principles theory that derives the coefficient of friction from quantum mechanics and statistical physics? No, not yet. After 500 years. After 500 years, not yet. There's still something mysterious about two surfaces in contact. Something that resists our complete understanding. Something that lives in the gap between the atomic and the macroscopic, in the emergence of simplicity from complexity, in the way that a single number can summarize the behavior of a billion interacting atoms. Mystery solved? Not quite. But we know more than we did. We know that static friction is not a fixed force, but a reactive one. We know it arises from the collective strength of asperity junctions. We know the transition to sliding is a rupture, not a threshold. We know that contact aging makes interfaces stronger over time. We know that at the nanoscale lattice geometry can eliminate friction entirely. We know that thermodynamics demands that sliding produces heat and increases entropy. We know that the simple law is a map, not the territory. And we know one more thing. We know that every time you stand still on solid ground, you are being held in place by the same physics that holds continents together. That the quiet stillness of your feet on the floor is maintained by thousands of microscopic bonds, constantly forming and reforming, in a dynamic equilibrium that looks like nothing from the outside, but is at the microscale a furious and beautiful negotiation between surfaces. You don't fall. You don't slip. You stand. And beneath you, at a scale you cannot see, the atomic world holds its breath. That's static friction.